Recall from a video corresponding preceding class, if we have a source emitting waves and we have two detectors, one at a greater distance from the source than another, if we take the signals that we get from the two detectors and mix them, then whether they reinforce constructively or destructively, whether this one tends to build on top of this one or to cancel this one or anywhere in between, depends on how much further this is than this, and specifically on how many wavelengths there are in this path difference. How many wavelengths further is this detector than this one? They tend to reinforce if the path difference is a whole number of wavelengths, because that will bring peaks into this one. At the same time, peaks are coming into this one. Even though it's a later peak, you're still going to have a peak reinforcing a peak. They tend to cancel if the path difference is a whole number of wavelengths plus half a wavelength, because that extra half wavelength brings valleys into articulation with peaks, and you tend to get cancellation. So that this is the condition for what we call constructive interference. Path difference is a whole number of wavelengths. Or destructive interference, okay, path difference equal to a whole plus half number of wavelengths. I'm going to have to close the door here. Animated conversation at the door across the hall. Looks like a nice bunch of kids, and I've done the same thing, so I'm not going to throw any stones. Okay, so anyhow, we have the condition for constructive and destructive interference. Okay, now, there's other situations in which this can happen, one being the two-slit situation. Okay, so things have gotten a little bit messed up here, but what I have here is a partition with two holes in it. Imagine a wall looked at from above, and we got two doorways. So that a series of wave crests coming along here in a direction perpendicular to that wall will encounter the wall and create a pair of synchronized disturbances at these two slits, and those disturbances then spread out along concentric half circles in this case, because they're not going to come back through the wall. Okay, so and we have the same thing here. Okay, so we're going to have waves coming out. Now, if we try to detect these things here, okay, then we have the distance from here to here, the distance from here to here. Those two distances are different. Now, it's kind of been obscured by everything else I drew, but I've drawn an arc. You can kind of see it, dotted line here, an arc at this distance from the common point. We see that this arc comes along here, and the distance from here to here is longer than the distance from here to here by this much. Okay, this arc represents this distance from the point. This distance is a little longer by this much. So here you have a path difference. Now, there's another situation. This point might be pretty close to these slits. We'll call them slits. They're openings. Okay? If we want to observe the result of these two, the result of the wave that comes through these two slits as it combines at a distant point, okay? Well, the paths to a distant detector are nearly parallel. If the detector is 1,000 times as far from this wall as the separation of these 2 points, then you really don't have much difference in this direction and this direction. So that we can say that the path to the distant detector from this point makes angle theta with the normal direction. Okay, now I've drawn a normal direction, direction perpendicular to this wall or this, whatever this is, coming out here to perpendicular, and I measure theta with respect to that. And similarly down here, the normal direction and theta measured relative to that. These angles will be nearly equal, so we'll call them both theta. Now, question is, what's the path difference from here to the detector as opposed to from here to the detector? Well, if we draw a line perpendicular to these two nearly parallel paths, okay, so we draw it perpendicular to this one, and it's approximately perpendicular down here. Let's see if I can get away with, yeah, I can get away with sketching that right angle as well. Okay, then the distance from here to the detector is going to be the same as the distance from here to the detector, just because of the perpendicular and the parallel and all that stuff. And again, simple geometric argument that I'm not going to detail. That means that the path difference is this. This ray has this much further to go to get to the detector than this ray. Okay? Now, I've drawn the triangle somewhat bigger so we can label a few things. First of all, I've labeled A. A is the distance between these two slits. So that's going to be this side of the triangle, clearly. We have this side, which is perpendicular. This side is along this ray, so it's perpendicular to this side. Here's your perpendicular. And here's the path difference. So this is the path difference. I'm going to go ahead and make this red. There's your path difference. And you can verify a couple of things. One is that this angle here is the same as this angle. And it's easy enough to see why. This side is perpendicular to this normal line. This side is perpendicular to this path of the ray. So that this side and this side being perpendicular to two lines that make angle theta, they have to make angle theta. Very simple geometric argument. Okay, so the path difference is then this side, and that side is, well, this is the hypotenuse. It's opposite the right angle. Here's the angle theta. This is the side opposite the angle theta. This is a hypotenuse. Very simple argument tells you that the path difference is therefore A times the sine of theta. This side is A times the sine of this angle. You can visualize changing this angle so that these parallel lines move further and further down this way to a detector that's more goes from this direction to this direction. And it's clear then that this triangle is going to expand. That this side of the triangle is going to get bigger and bigger. So that at some angle, the path difference will just be equal to half the wavelength. Now let's see, what's the wavelength? If the wavelength is the distance between these crests, then the wavelength is about this, and that path difference looks like it's pretty close to a wavelength. Now at an angle that's close to but not exactly half of this angle, this side will thin down to where it's only half a wavelength. Now at half a wavelength difference, the peaks of one are going to meet up with the valleys of the other. And you're going to have destructive interference. If this is light through two slits in whatever, piece of paper, whatever it is, then out at this distant point, you're not going to see a whole lot of light coming through. If you move to this angle, then if this corresponds to one full cycle, so that path difference is equal to a whole wavelength, then the peaks of this will meet the peaks of this when they finally meet down there at the detector. If we then increase the angle, well, this side is going to get bigger and bigger, and will at some point become 1.5 wavelengths. So that now this is going to be 1.5 cycles behind this one. And again, you're going to have valleys meeting peaks. Make the angle a little bigger, this distance gets bigger, and now you're 2 wavelengths out of phase, and peaks are going to be meeting peaks again, you're going to have constructive interference once more. So you should understand that. The mathematics is simple. This A sine theta is a very simple formula. It's equal to the path difference. Path difference, a whole number of wavelengths, gives you constructive interference. Path difference, a whole plus half a wavelength. A number of whole wavelengths plus half a wavelength gives you destructive interference. Mathematics is fairly simple, but you want to have the picture so you understand what's going on.